Thus far, we've been considering all surfaces to be chemically homogeneous and absolutely flat. In real life, of course, surfaces are rough. So what happens to the apparent contact angle when we start having rough surfaces? We can define roughness as the area divided by the flat area. So in other words, if we just look down at our area and assume that it's absolutely flat, how many square centimeters would that be? Versus actually going down and measuring the surface at a nanoscopic level. What's the actual area when we factor in all the hills and valleys? And the actual area is going to be greater than the projected flat area, so the roughness is going to be greater than 1. Let's see what effect this has on contact angle. So first, let's look at a case where we have a surface that is wetting. And let's draw in the plane representing the edge of the surface. And if we have something wetting, we know the contact angle is less than 90 degrees. So we'll imagine drawing something normal to the surface here at 90 degrees. So the contact angle is something less than that. So our water droplet or a liquid droplet would come out at something less than 90 degrees. And we could draw a similar picture over here where we have 90 degrees, and then we have our droplet with a contact angle of something less than 90 degrees. And our droplet will look something like that. So if we look at our water droplet here, so here's our water droplet, something that wets this rough surface. We can see there's two different angles. The first is the apparent contact angle that we measure. And the apparent contact angle is going to be the angle between the blue line and the red line. So we can see the actual microscopic contact angle is between the material at a nanoscopic level and the liquid, and it's less than 90 degrees, but it's still substantial. That's the actual contact angle. But that's not the one we'd measure using a contact angle goniometer. Instead, we would get this much smaller angle with the apparent surface, the surface on a macroscopic level, and the liquid. Notice that theta observed is much smaller than the actual theta. So what happened is we took something that was wetting, had a contact angle less than 90, and made it more wetting. So wetting materials become more wetting when we roughen them. Now let's look at something that's non-wetting. In the non-wetting case, we still draw 90-degree angles and say, okay, we're non-wetting, so we have to have a contact angle somewhat more than 90. So we'll make a contact angle somewhat more than 90 on both sides. Make our droplet. So here's our droplet of liquid. So in this non-wetting case, we can compare the observed contact angle and the actual contact angle. So we look up the observed contact angle. It's going to be between the mathematical plane and our liquid. So there's our angle. And if we look at theta actual, it's between the material itself. And look at the angle, we can see it's only a little bit more than 90. So we can see in this case that theta observed is going to be greater than theta actual. So the contact angle actually increased. It became more non-wetting when we roughened. So notice, in non-wetting, we became more non-wet when we roughened in terms of the observed contact angle. That would be the one we'd actually measure. And in the case of wetting, we became more wetting when we roughened. So roughening accentuates the pre-existing character of the material with respect to contact angle. This is summarized in the Wenzel equation. The cosine of the observed contact angle is equal to the roughness times the cosine of the nanoscopic actual contact angle. So let's do an example. So we have a surface that's already wetting with a contact angle of 30. We want to make it perfectly wetting. We wanted to put that into English. What do we mean? We mean that the observed contact angle has to be equal to 0 degrees. So we can solve this for R. So R, we can see, is going to be the cosine of theta observed divided by the cosine of theta. So in our case, this is the cosine of 0 degrees all over the cosine of 30 degrees. And we plug those numbers in, we can see this comes to 1.15. So really only 15% more area than the original surface. So this is not really that rough, and yet we were able to make it totally wetting. This is why Wilhelmy plates are bead blasted to make them rough. When a Wilhelmy plate's flamed, there's a thin layer of platinum oxide on the surface, which has it's quite wetting. It has a very small contact angle, but then because it's bead blasted, it makes the contact angle with water approximately 0.